Hi everyone! So today we are going to be talking about angular momentum. So when we have a particle of mass m that has a linear momentum denoted by p, which is equal to mass times velocity, and that has an angular momentum L with respect to the origin O as it passes through a point A distance r away from O. Wow, that was a lot of variables there. But basically what's happening here is we measure the angular momentum relative to an origin O. So we have a linear momentum of a particle, and then we're measuring angular momentum from the distance away from whatever point we're measuring the angular momentum from, which is that r distance r away from O. So our equation that we get here is that the angular momentum L, which we can see is a vector, is going to be equal to r cross p, where r is that position vector, the distance from the origin or whatever point we're maybe rotating around or measuring from. And we have a cross product with linear momentum p, which is mass times velocity. Now, of course, because velocity is the vector, we can kind of factor out a mass term here because p is mass times velocity. Mass we're factoring out here to kind of show you that the cross product really is r cross v here. So this is our equation for angular momentum. So where r is the position vector of the particle with respect to O, and as the particle moves relative to O in the direction of its momentum, the position vector r rotates around O. Now it is important to note here that to have angular momentum about O, the particle doesn't actually have to rotate around O. Okay, so rotation does happen usually when we're talking about these problems, but in order to have an angular momentum about a point, the particle doesn't actually have to rotate about that point. So if we're talking about the direction of angular momentum, we use the right-hand rule just like we do for torque. So it's very, very similar in that direction. So we're using the right-hand rule to determine the direction of angular momentum. And the reason that we can also use the right-hand rule for angular momentum is because just like torque, angular momentum is also a cross product. So what we do here is we're going to point our fingers in the direction of r, because that's the first vector in our cross product, sweep the fingers or curl the fingers in the direction of the momentum or the velocity vector, and then the thumb points in the direction of our angular momentum. So if we have something like this would be our plane here. Say that this is the point we're measuring it from, and our point is here. So this is our r vector. I would point my fingers in the direction of r, and then say the momentum is going that direction. I would curl my fingers in the direction of momentum, and my thumb points upwards. So it's going to always be perpendicular to that plane here. So the magnitude of our angular momentum will be r times mv times the sine of theta. Again, we're using the sine of theta because it is a cross product here. And so it's going to be at a maximum when that angle theta, which is the angle between the r vector and the velocity vector, when that angle is 90 degrees or they're perpendicular, then we have a maximum angular momentum. So that angle, like I said, is the smaller angle between r and p, and thus v, when the two vectors are tip to tail. So the units for angular momentum are kilograms times meters squared divided by seconds, which is also equal to joules times seconds. So that's our units for angular momentum. Now, the important things here is that number one, angular momentum has meaning only with respect to a specified origin or a specified point that we're measuring it from. So that's the only way we can get this r vector is if we're measuring the angular momentum about some point. And then number two, the direction is always going to be perpendicular to the plane formed by the position and linear momentum vectors r and p. So again, like I said, if this is the plane, this right here is our r vector and our p vector is directed this way, that r and p are in this plane, and then the angular momentum was perpendicular to that plane. So it could also be downwards, perpendicular to the plane, but it's also they're always going to be basically perpendicular to one another when we're talking about, the actual angular the momentum that matters, which is why we use sine of theta, right? We want that perpendicular momentum vector, just like we talked about with torque, because that's a cross product as well. Some people like this method too, where the pointer finger points in the direction of r, the middle finger would then point in the direction of the linear momentum or velocity, and then your thumb points in the direction of angular momentum. So that's another option there, and you can see that all of those fingers are 90 degrees to one another. So let's do this example really fast just to kind of talk about what angular momentum is and what really it depends on, basically. So we have in this figure right here, part A, particles 1 and 2 are moving about point O in circles with a radii of 2 meters. So 2 has 2 meters and 4 meters. And then it says in part B, particles 3 and 4 travel along straight lines at perpendicular distances of 4 meters and 2 meters. So that means just when particle 3 gets here to this perpendicular distance, that's your 4 meters. And then this, if particle 4 was here, that would be 2 meters. Now, these are going to be the r distances that really matter here, because of course, if we use our angular momentum equation, r cross p, right? That cross product signifies that this angle between r and our linear momentum, we would then have a sine of that angle right there. So if that angle was 90 degrees, so when this particle then gets here, then we are really just concerned with this r vector, and then that linear momentum will be the same there. So that will be this r vector cross p, which will then just be r times the linear momentum there, because here the sine of 90 will be 1. All right, so that's all they're saying there. So really what we're looking at here, because it goes on to say particle 5 moves directly away from O, all 5 particles have the same mass and the same constant speed. So since they have the same mass and the same constant speed, they have the same linear momentum. So really all we're comparing here are our r vectors, which is the distance from that rotation point, or just the point O, okay? So the ones that have the greatest distance from point O are going to have the most angular momentum. So we can see that 1 and 3 are both going to have 4 meters away from point O. So those are going to be the greatest magnitude of angular momentum. So 1 equals 3 will be our greatest. And then both 2 and then this perpendicular distance of 4 both have 2 meters. So that will be the next greatest. So then we'll have 2 equals 4. That will both have the same magnitude of angular momentum about point O. And then last but not least, particle 5, since it's moving directly away from point O, we can see that the angle between that linear momentum vector and the r vector here, that angle is 180 degrees. So because it's 180 degrees or 0 degrees, because they're both pointed in the same direction, the sine of 0 or the sine of 180 is 0. So this particle actually has no angular momentum about point O. So it's 1 equals 3, and then 2 equals 4 for letter A. Now letter B, if we're finding which particles have negative angular momentum about point O, this is the same rule for torque. So something that has a negative angular momentum will be something that is rotating clockwise or could rotate clockwise about the point. So we can see that 1 rotates counterclockwise, so that's positive. 2, though, rotates clockwise, so that's a negative angular momentum. And then we can see 3 here. If it were to rotate about point O, it would be clockwise, so that would also be negative. If 4 were to rotate about point O, that would be counterclockwise, so that would be positive. So for part B, it would be 2 and 3 for our answer there. All right, so we can also talk about Newton's second law in angular form. So if we write this in terms of momentum, we write the net force equals our change in momentum over change in time. Now this works because, of course, momentum, linear momentum, is mass times velocity. So here, velocity over time, or change in velocity over time, or dv over dt, that of course is acceleration. So that would be mass times acceleration, which is why this equation works. So The relationship that we can then see between torque and angular momentum would be this right here. So we get torque is equal to angular momentum over time, or dl over dt. Again, this right here is this linear force, but in angular form. Okay, so this is our equation that we get for the net torque. So it's going to be the change in linear momentum, or sorry, change in angular momentum over change in time. So, and this makes sense, right? We learned about how a force during a certain period of time will equal a change in momentum when we talked about impulse in our linear section. So here, this is the same thing. We can get an impulse type thing from a torque over a certain period of time in order to get a change in angular momentum. So to change angular momentum, there has to be a torque, is basically what I'm saying. So the vector sum of all the torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. And this equation has no meaning unless the torque and the angular momentum are defined with respect to the same point, which is usually the origin of the coordinate system being used, or just that reference point that these things are maybe being measured against or rotating around, or whatever we're talking about here. So it might be an axis of rotation, it might